Hi everyone, it's Mr. Glover here. We're just going to get ready to do our next set of, next couple questions. So the idea today is I'm going to keep the video fairly short because I know it's a weekend and I don't expect you to watch a long 40-minute video today. What I want to do is work through a couple of problems based on using combinatorics to calculate probabilities. And this is going to be the topic we work on for the next couple of days. So let's read through the first one. 4 boys and 3 girls will be riding in a van. Only 2 people will be selected to sit at the front of the van. Determine the probability that only boys will be sitting at the front. So let's list out what we know. 4 boys and 3 girls. So we've got 4 boys and we have 3 girls. If we join those together, we will have 7 total people. We also know that only 2 people will be selected to sit at the front. And the question wants to know the probability that only boys get selected. Okay. The other thing we need to ask ourselves is, does the order matter in this question? And while you might think it does because we're putting them at the front of the bus and being put there is different than the back of the bus, we're not choosing the order for everyone. We're only picking 2 people that get to sit at the front. It doesn't matter if Johnny or Bobby sits first or second, they're both at the front. So this is a question where the order makes no difference. Since the order doesn't matter, what that tells me is this is a combination problem. So let's go ahead and we can calculate the number of favorable outcomes. Okay, so the number of favorable outcomes is going to be equal to the number of ways that we can select 2 boys. Okay, to do that, we're picking 2, and we're picking out of a pool of 4 people. So if this population of 4 boys is N is 4, and 2 we're selecting is R, this is a 4 choose 2 calculation. So we can do this by hand or we can use a graphing calculator. 4 choose 2 is 6. Okay, so that's the number of favorable outcomes. We now have to go and calculate the total number of outcomes. So let's move over here. Number of total outcomes. And the number of ways to do that is the number of ways to pick 2 people, period. Regardless of whether they're male or whether they're female. So in this case, we have a population of 7 to pick from, not 4 anymore. So we're still choosing 2, but we're choosing 2 out of 7 this time. So 7 choose 2, you can calculate that. 7 choose 2 is 21. So that means there's 21 ways to pick the people, and 6 of those ways would be with 2 boys. So we want to calculate our probability now. Probability of selecting 2 boys is given by the number of ways we can do it divided by the total number. 6 ways to pick 2 boys. Divided by 21 ways to pick total. So 6 over 21 gets me a probability of 0.286. If we want to turn that into a percentage, we have to multiply by 100. So 0.286 is 28.6%. So what's the probability that the 2 will be boys? Well, it's 28.6%. Roughly 30% of the time, you'll pick 2 boys at random. Now, we should probably talk a little bit about sort of the context here. We're assuming that everything is completely random. There's no bias whatsoever. So this would be the scenario where you put all of their names in a hat and you just draw 2. 30% of the time, it's going to be 2 boys. We didn't calculate specific people, but this is just for 2 points. All right, one more question. So Kansas is playing poker for choice today. She draws 5 cards from the deck at once. She wants to know the probability of getting aces and 1 heart, or 1 other heart. Okay. So let's see here. We have 5 cards to pick from, so N is going to be 5. Probability of getting 4 aces and 1 other heart. So in the deck, there are 4 aces. So we're really, when we're drawing the 4 aces, we're actually pulling from a population of 4. There's not very many to choose. There are 13 of every suit in the deck, and there are 52 cards total. Okay, so we're going to have to do the same kind of thing where we calculate the favorable outcomes, the total outcomes, and then divide them. And you will see that there's not a lot of favorable outcomes in this scenario. So start with favorable outcomes. Maybe we'll split this up first, actually. There we go. So this will be for favorable outcomes. This will be for total outcomes. And this will be for the probability. All right, so we want 4 aces and 1 other heart. So the number of outcomes is going to equal the number of ways we can calculate pick 4 aces and 1 other heart. All right, and then the question becomes, does the order matter? In this case, no, because you can order your cards however you please, and it makes no difference what order you have them in. So it's a combination question. Since we're picking out of 4 aces, 4 choose 4 is the number of ways to calculate or to pick those 4 aces. 1 other heart, we have to be a little bit careful with. We're picking out of the 13 hearts. However, 1 of them was already picked for the aces. So we actually only have 12 other hearts to choose from. So this will be 12, choose 1. We can then go ahead and we can calculate these things. 4 choose 4 is simply going to be 1, but what we're interested in is the 12 choose 1, which is 12. So this is 1 way to choose 4 from 4 and 12 ways to choose 1 from 12. So there's only actually 12 hands that satisfy this requirement. It's really not very likely. Okay. So there's 12 ways, or 12 hands. If we want to go calculate the total, there's going to be a heck of a lot more. In this case, we just have to pick 5 cards out of 52. So the number of ways total is going to be 52, or we'll follow through the same as before. So we have 5 cards. This is going to be 52 choose 5, which is a lot of hands. 2,598,960. So if we want to calculate the probability, it's very, very low. Probability of 4 aces and 1 heart is going to equal the favorable outcomes, which is 12, divided by the total outcomes, which is 2,598,960. Which gives us probability of 4.62 times 10 to the minus 6. If we multiply by 100 to turn it into a percent, it's still an incredibly unlikely event, which is 4.617 times 10 to the minus 4. Right, so we could call it 4.62. We already rounded. If you want to turn this into an actual a bunch of decimals, we just move this over 4 spaces. So we go over 4.62. We're going to go over 1, 2, 3, 4 spots. So this would be a 0, 0, 0. So the probability in terms of percentages is 0.000462%. Not very likely. But if you think about it, we just asked for an incredibly rare hand. We asked for 4 of a kind with aces, and we had a specific other suit as well. That is not a hand you are likely to expect very often in a poker hand. So, I mean, it's kind of what we'd expect. If you want the total number of ways to get 4 aces, period, you could calculate, you could go over, and instead of going 12, choose 1, you could do whatever's left in the deck, so 48, choose 1. Or you could just take this and you could just multiply by 4, because it's like you have cases, right? It's like you'd have the case of having one other heart, or one other spade, or one other club or diamond. So basically you're just multiplying this by 4. It means your probability will also increase by 4, but you're still going to be incredibly unlikely to get it. It's going to be 0.006 or 0 or 16 or 17. Still super unlikely. But it is possible. And that's why in poker, 4 of a kind is one of the rarest hands. So I think we'll stop here. We've kind of gone on a little bit of a tangent talking about cards and probabilities, but the basic idea with all of these questions is to calculate the favorable outcomes, calculate the total outcomes, and then divide them to get your probability. So that's where I'm going to end the notes today. I wanted to keep it fairly short. So there's no extra homework today. Tomorrow, we will talk a little bit about combinatorics again. Tomorrow, we'll solve a few more problems in our notes, and then we're going to move on to mutually exclusive events. So I hope you have a good rest of your day. I will see you all tomorrow, and we'll do a few more problems. So bye for now.